Can everybody hear me? Okay, cool. So, my name is Chen Feng. I'm an assistant professor jointly between the civil engineering department and the mechanical engineering department. My last name is AI Force. It stands for Automation and Intelligence for Civil Engineering. This is the lab logo designed by the students working in my lab. I joined NYU since 2018. Before that, I was a research scientist in Boston in a lab called Mitsubishi Electric Research Lab for 3 years, working on computer vision and robotics. So, today I want to give you a brief overview of what I do in my lab and what my colleagues do in the civil engineering department in this disciplinary called construction engineering and management. My introduction will be more leaning towards the engineering aspect, as the name robotics, automation, and intelligence already suggested that. So first I want to show this image to pretty much give a historic perspective of construction engineering. Anyone know when this photo was taken and where it was taken? Well, because we're at New York, so this must be somewhere in New York. No, that's a good guess. No. So, well, try to guess the time, like 30, 50, 80 years? Okay. So this photo was taken nearly 90 years ago, okay? And it was about 850 feet above what is now called the GE building in the Rockefeller Center, okay? So during your next, the spring break, try to visit that place. This will be a pretty cool place to be. This is when they were building, these are 11 iron workers building the skyscraper there. So now I want to switch to another perspective because I'm a science fiction fan. So this is a science fiction view of what construction in the future, I don't know how many years, maybe 100 years, hopefully I can see that day come, which obviously is making an analogy between the previous image, right? So, so this is what I do as my research. In short, it's construction robotics. You may be, well, we're not here yet, so I want to first show you some videos which describe what is the state of the art, what is going on in the field of construction robotics. Well, the first video is done by Microsoft. You might be feel surprising to see actually Microsoft's business is related to construction. What they're doing is combining artificial intelligence, computer vision technology to improve the intelligence level of construction job site. It's typically, like traditionally, it's a pretty crowded and not well organized job site. But with surveillance cameras powered by artificial intelligence, we can do more efficient operation on the job site. The second one is a startup. It was, I think this startup is in Ann Arbor, Michigan, where I got my PhD. They're using this kind of mobile robot with laser scans to scan a construction job site so that the managers will be able to get daily update without actually going to the job site. And it can give more detailed, more accurate estimation of the progress. This one is actually what I really like. It's performing 3D concrete printing using robots. Okay, my lab actually recently got funded by the NSF to perform, to look into the algorithm and theoretical aspect to improve the efficiency and accuracy of 3D printing with mobile robot. This one is another startup in I think it's in California. They're using the self-driving technology to enable autonomous excavation and those construction equipment so that they can work. See this one. This is a real video, by the way. It's not fake video. That what people can do already with today's technology. This one is in Australia that does automatic bricklaying precisely into any curve, like very complex, geometrically interesting structures. Okay? So these videos, I want to show them to give you a modern perspective of the construction or civil engineering quick overview. All right. A more futuristic view of construction or construction robotics. This is a figure that I found on by this company, Autodesk. So many of you will be or already have been using the product for this company to do the AutoCAD or building information modeling softwares. So this is what that company believes in the future. The construction site will be something that look like this. We will have a lot of on-site sensors. There may be static or installed on drones. They will be interconnected. We will have robots doing repetitive and dangerous tasks for us. All right. So what my lab does is to really go from here to here, and eventually to the robot that you just saw. Okay? I prepared 9 videos that was done in my lab or during my PhD years. I gave the numbers, so if you're interested in any one of them, just shout out the number and I'll explain. Okay? 3. So I've been doing this lecture multiple times. This is the 3rd time I'm doing this. Somehow, always people start with 3. There must be some reason. Okay. So number 3. This is what we're doing. Is called a semantic edge detection. This is a work that I did in Boston 3 years ago. The idea is to put cameras on autonomous driving vehicles. And then develop neural network models to analyze the scene in front of the vehicle. So this vehicle can be self-driving cars. In civil engineering, it can be installed on a truck or excavator so that the machine gets a better understanding or more holistic understanding of the scene. Here are the color codes. So first of all, the white pixels are background pixels that are not of interest to us. We're interested in the boundaries or the edges because, for example, this red edges, they mean the edges formed between the road and sidewalk. Right? Different color means different type of edges. Some edges are between road and human, road and car, car and human, car and building. So with this kind of level of understanding, the self-driving cars or autonomous excavators can be more intelligent. It requires less skill to operate. Okay. Any other numbers? 1. Number 1. This is a work that this is a pretty old work that I did maybe 7 years ago in Michigan. So that was a scene in Ann Arbor. That's my apartment. I really missed it. What we're doing there is an algorithm that can efficiently analyze the point cloud captured by a device called Kinect. How many of you play Xbox? How many of you bought Kinect? So you've been using that, right? You can. I remember there's one game that I played which is to imitate the dancing, right? The dancing game, where you need to use the Kinect to track your 3D movement. We're using the same device, and this device will capture the 3D information of the room in front of the camera, and then we will analyze, we will detect the planes in front of you. For example, the ceiling, the wall are all segmented, okay? And this technology is used in augmented reality, in robotics. It's a patented algorithm, and I believe it's being used by Google and Magic Loop, those augmented reality glasses. Okay. In construction, well, in civil engineering, we can use this technology to automatically analyze the 3D laser scans of the environment. For example, if I have a laser scan device that scans this room, we can then send the point cloud returned from the device to this algorithm, and it will tell you where are the planes. And with that, we can simplify the model and create what we call as building information models automatically without a lot of human user tedious operations. Okay. Any other numbers?
2.
2. Okay, cool. I'm glad you asked this. This is a recent work published last year. It's called deep mapping. The idea is we put some laser sensors on a mobile robot. Again, this robot can be a self-driving car. It can be an autonomous truck or excavator. And then, in order for those vehicles to localize themselves in a map, in an environment that it has never been visiting before, we use this neural network model to automatically align multiple frames of point cloud. Here, the color means different frames of point cloud. And the network will automatically align the point clouds without any human intervention. Okay? Previously, before this algorithm, you need to do a lot of human manual work in order to go from a random initialization to the final aligned. So this is a 2D map. Imagine it's a 2D blueprint of a job site. Okay? Other numbers?
8.
8. Glad you asked this. Anyone see this? Okay, I'm not too old. So I'm a big fan of animation. So this is from the Disney movie, and the robot is Baymax. It's a soft robot. Soft robot means robot that are made from flexible and soft and compliant materials, so they're safe to work with. They're not like this type of robot that can easily crush you, okay? Soft robots are safer, but the challenge is you cannot easily perform something called state estimation and control for soft robot because it's a continuously deforming surface. What we do is, again, taking advantage of artificial intelligence to create a mathematical and computable model for Baymax, and we actually make this robot. We bought a toy from Amazon, and then put cameras inside, and this allows us to. This is what the AI or deep neural network is able to predict the 3D surface accurately without using any external sensor. Okay? So we're going to showcase this in April in DC in a science event. Okay. Any other number?
0.
0. So 0 use the algorithm in 1. It is again using Kinect to scan your office, your apartment, and so Kinect itself is about a few $100s. With this kind of low-cost sensors, we can create an accurate 3D model for a lot of purposes. Maybe in the future when you're buying your own apartment, you want to design, like, where should I put this furniture? You can first use this technology to scan your room and then plan for the interior layout. Okay? Any other number?
5.
5. Oh, 5. I like this one. This one is the enabling technology for the Baymax one. It's called FoggyNet, where we essentially are teaching a neural network to understand geometry by paper folding. So we teach a neural network to automatically learn how to fold a piece of paper onto any type of shape. And through this, the network has the ability to understand geometric shape instead of just images, right? When typically when people are thinking about AI or deep neural networks, they're thinking about an image with a lot of cars and going body loss. But what we're showing is you can do a lot more than just processing images. Okay? Other number I just heard? 4. 4 is using the technology from 3, where addressing a problem of place recognition or navigation in an urban situation. How many of you have actually driven in a big city like New York? Okay. If the first time you drove in those places, you must feel puzzled because the GPS will go crazy in some of the situations. And for 1 minute it will be in Manhattan, the next minute it will be, I don't know, somewhere near Brooklyn. And that's really problematic. What we're doing is using images, which is more close to humans' ability of navigating and recognizing where we are. We don't receive satellite signals, right? So the reason why satellites, the GPS will go crazy is in urban areas, there's something called urban canyon. When you have a lot of skyscrapers, the satellite signals will suffer from something called multi-path reflection. You have the signal will reflect multiple times. That will create errors in the positioning algorithm. So we bypass that by putting cameras on the vehicles, and then match the image with the previously localized image. And as long as you can match the two images, so this is a query image that's what you see right now in your car, and then the system will look for the most similar image in the database where we already know where that image was taken, and then you can localize yourself. Okay? I guess this is the only one that is not explained, so I'll just explain this one. This one is my PhD work. I did it in University of Michigan in collaboration between Department of Architecture. So I work with a bunch of architects and roboticists, and myself is a roboticist. What we're doing is to go from the algorithmic architectural design through robotics and computer vision, here is a camera, to automatically execute the building plan and build a curved wall, okay? Without any human intervention. The challenge is, when you future hopefully join the civil engineering department, you will learn that to construct those irregular shapes is very challenging, okay? So if civil engineers get to decide, we will just build boxes, okay? But architects don't like that. They want to build all kinds of weird shapes, and it's really challenging for us to do it efficiently. That's why we're bringing robots. Robots can do this efficiently and accurately, but the current challenge is the robots are not smart enough. So with my lab's research, we're trying to make construction robots more efficient and smart so that our future construction work can be safer and more efficient. Okay? So with all those research, I hope in the next 20 and 30 years, we can really achieve autonomous construction robots with those spatial, what I call spatial AI technologies. Again, this shows I'm a really Disney or animation fan, right? This is a Wall-E robot. I always use this to motivate. So my goal or my mission or my last mission is to make sure in the future we can see those type of cute little robots work with construction workers on Earth or even on the Moon and Mars. Okay? With that, I think.
Cool. Okay, now for something totally different. So hi everyone, I'm Andrea Silverman. I'm an assistant professor in the Civil and Urban Engineering Department. Oh, okay. And I'm an environmental engineer. Who here has heard of environmental engineering before? Wow, that's awesome. Okay. Well, do you guys know what environmental engineers do? I guess you've heard of them. Who here knows what an environmental engineer does or has an idea of a couple people? So what does an environmental engineer do? The definition that I typically like to give is that we were very interdisciplinary people. So environmental engineering, I guess in engineering in general, we like to say are the applied sciences, and environmental engineering is quintessentially the applied sciences. We like to study the fundamental sciences, so biology, ecology, chemistry, geology, mix it with soil science, fluid mechanics, principles of engineering, have a policy aspect, and we put that all together to try to develop solutions to environmental problems and therefore protect public health. And I really want to, in case you guys have never heard about environmental engineering or environmental science again in your careers, I just want to highlight for all of you, if you have a contaminated environment, it is very hard to have a healthy population. And so while we are environmentally motivated, the deeper motivation is human health, okay? So that's our ultimate goal. We do a ton of different things. This is just a couple of them. We work in water and wastewater treatment. We work in air pollution, air quality, hazardous waste management, cleanup of contaminated sites, like Superfund sites, like the Gowanus Canal, the Hudson River Superfund site, et cetera. We work in that. Solid waste management, pollution prevention, period. And we also have an important policy management side. One thing I'll say, Jack asked us to say a little bit about, how we got here. I remember being in your shoes. I was a first-year student at university, and I had no clue what I wanted to do. I'm a really indecisive person. There was too much that I was interested in, and I ended up getting drawn to environmental engineering because I didn't have to pick. I got to do a little bit of everything. So we get a really nice basis in all of these fundamental sciences and use it for sort of the societal good. So in these realms, we do very different things. We don't always speak the same languages. I work specifically in the water and wastewater treatment side. And what brought me here was because of the obvious human health aspects. Plus, there's some really cool process engineering that goes into it. So the science is cool and interesting. The applications are incredibly important. So just to give you a quick view of water and sanitation, I'm going to look at New York City. We have one of the best water systems in the country and in the world. We are incredibly fortunate that our water supply actually comes from these pristine sources up in the Catskill, Delaware watershed and the Croton watershed. And the DEP, the Department of Environmental Protection here in New York City, is our water and wastewater utility. They pipe all this water down to us through a series of aqueducts. They treat it right before it comes to the city, and they get it to all of our houses and the buildings that we live and work in. We're so fortunate. We are such a huge city, and to have such an amazing water supply is really an incredible path. But one thing I want to highlight to you guys is that once this water comes to us, most of it goes down the drain, right? In a variety of different ways. In the sink, if we have a washing machine or a dishwasher, in our showers and our toilets, right? So all of the water that we use, or I think most of the water that we use, becomes wastewater. And so you can never bring water to a city without thinking about where it then goes. You can't just have wastewater sitting around. So I like to, highlight also what is in wastewater, because I said I was in water and wastewater. I am a little bit more on the wastewater side, because it's an incredible challenge. So when we think about what's in wastewater, there's definitely water in wastewater. There's also the things that we pour down the drain. So, if you're using soap, if you're cooking, you have oils, food scraps. I also like to say anything that's on your body, that you put on your body, there's like lotions, hair gels, any type of personal care product, that ends up in wastewater as well. The things that we ingest and excrete go into wastewater. So we have homeostasis within our bodies. So we do burn nutrients and burn calories, but a lot of nutrients still end up leaving our bodies. If you take any type of drug, whether it's pharmaceutical or otherwise, that ends up in wastewater. We only metabolize a small portion of it, so we have a lot of drugs in our wastewater. Salts, antibiotics, etc., all end up in wastewater we have to deal with. And then the big thing that my work focuses on is pathogens. So whenever we're sick, we are excreting whatever organism made us sick. And that's going into wastewater as well. And that's either through fecal matter or urine. Wastewater treatment is incredibly important because we want to make sure that all of these contaminants don't end up in water bodies, because those water bodies that surround our cities are the ones that we either bathe in, like the recreational waters, sometimes they're drinking waters, sometimes we fish in them, so we need them to be clean. So the New York City Department of Environmental Protection has also done incredible work having wastewater treatment facilities. So we have 14 facilities spread throughout the city, and they treat 1.8 billion gallons of water a day, which is an insane task, and we're just, very, very fortunate to have them. We are here, where are we? Yeah, we're here. So number 9, the Red Hook facility is what treats our wastewater from this campus, and it's located in the Navy Yard. It's a really cute facility. If any of you ever take my environmental engineering class, we visit this facility. This is the biggest wastewater treatment plant in New York City. It's in Greenpoint. It's Newtown Creek. If you talk to any of the students who have taken my course, they love this trip because you get to visit this super cool plant. And so we are doing a pretty good job in treating our wastewater. There are still a lot of challenges that exist, which kind of fuel a lot of the research that we're doing. But in addition to working in the context of New York City and the United States, the work that I do also focuses on parts of the world that have less resources. And so one of the challenges that we're facing sort of in a global wastewater perspective is that there's still 2.4 billion people who don't have access to what we call an improved sanitation facility. So they don't even have like an improved toilet that they can use. Of those that do have an improved sanitation system, there's another 1.5 billion that don't have access to sewage treatment. So put this together, that means that half of the world's population excretes, makes wastewater, excretes whatever they're excreting from their bodies, and fecal matter, urine, and that goes directly into the environment with no treatment whatsoever. And this creates a lot of challenges. The big challenge that we focus in my lab is that waterborne illness can be spread through pathogens that just end up in the environment. So in terms of, so this is slightly old data, but it's around the same. If we look globally across all ages, what we find is that diarrhea is the 10th leading cause of death globally, and it's the 3rd leading cause of illness. If you were to look at children under 5, the ranking would increase because the children could be more vulnerable. So this is a big motivator for the work that we do in my lab. So I've given you that kind of high-level environmental engineering perspective. I'm going to tell you a little bit more about what we do. And I will say that the work that I do in my lab is a little bit niche, but definitely fits into the broader picture of environmental engineering in terms of the tools that we're using. So in my lab, because of these challenges, we're trying to study and develop sustainable and appropriate wastewater treatment systems. Again, to have this environmental perspective, but also a public health perspective. We do this in 3 regards. We look at pathogens, so waterborne pathogens and disinfection. We are interested in natural wastewater treatment systems. And we're also really interested in human waste reuse and resource recovery, because that helps give value to wastewater treatment. So for low-income regions of the world where there isn't a ton of motivation or resources available for sanitation, we're trying to provide that motivation by assigning value to treatment. Okay, so first of all, what is a natural wastewater treatment system? So I showed you before, the Newtown Creek system is what we call an engineered treatment system, right? Really big, engineered, a lot of processes going on that require a lot of energy. Natural treatment systems are designed. We have design equations that dictate how we build them, but we design them to be like natural systems and to use natural processes for treatment. So this is one of my favorite natural wastewater treatment systems. It's a pond system in Nairobi, Kenya, where you have a series of ponds, so small ponds, these bigger facultative ponds, into these maturation ponds, where through that series of ponds you have sequential treatment processes that get us to a safer effluent. I will say Nairobi is a pretty modern city. This treatment system treats the waste of about 1 million people. It's really impressive. And these systems are not used only in places like Kenya. We also use these natural treatment systems in the US too. Australia uses them as well, so they're used in all over the world. This is what these ponds might look like on the ground. They look like ponds. But we are using design equations to design them. So one of the things we do in my lab is try to better understand the processes that are going on within each of these ponds so that we can then build better design equations so we get better treatment efficiency at the end. On the disinfection side, the main disinfectant in pond systems is sunlight. And so we focus a lot on bacteria, viruses, and we're looking at antibiotic resistance and antibiotic resistance genes. We try to figure out what the processes behind sunlight disinfection is, and we use these findings to develop design equations. On the human waste reuse side, and this is also thinking about pathogens. So for human waste reuse, typically the way that we're treating waste right now, we collect it in a treatment system, we treat it, we dispose it. But there's a lot of valuable products in human waste. So one of the ideas of human waste reuse systems is that instead of just disposing this waste, it goes to some sort of processing system. Maybe we then convert some of this human waste to energy, because there's a lot of embodied energy in fecal matter and in wastewater, and we can use that to power cities. There's also a lot of nutrients, so what if we process those nutrients to a way that's usable on farms and in agricultural systems? And I mentioned before, there's a ton of water in wastewater. So can we reuse that water either in cities or for agriculture? And as I mentioned before, hopefully we're developing, generating money that can then feed back into the upstream sanitation system, because it is not inexpensive to collect and process this waste. For all of these reuse cases, we have to think about the health risks. So if you're going to take human waste and put it on a farm, you need to make sure that you're disinfecting it first, so you're not then making people sick downstream. And so reuse happens in a number of ways. In the United States, we do reuse water. There's this purple pipe is the standard that we use for reclaimed water, and it's used for irrigation purposes and for toilet flushing and for industrial uses. And we have specific standards that are set to make sure that the health risks are abated. So we try to figure out how to treat this waste to meet those standards. We also create energy. So the Newtown Creek Wastewater Treatment Plant up in Greenpoint, these are its digesters. It has these beautiful digester eggs that, like, if you're ever on like the BC, you can see them. They glow like turquoise and pink at night. And they create methane that we can then burn and turn into electricity or put back into the grid as natural gas. So we are generating energy, right now. I mentioned that I work in other contexts as well. And to just give an example of some reuse cases, this is a company called Pivot that was in Kigali, Rwanda. And what they were doing is they were taking human waste, they were dewatering it, drying it, processing it in a number of different steps, and eventually they made a solid fuel product that was then used as a solid fuel for cement kilns to be able to make cement. And this was really important in Rwanda because Rwanda outlawed coal, and these industries needed a biomass fuel to burn. So this project worked out really, really well in providing a fuel for industries that needed it, and then it provided a value chain so that there was actually money to pump into the upstream system. Another example I have of human waste reuse comes from a company that I actually worked for before coming here. This company is called Sanergy. It's in Nairobi, Kenya, and what Sanergy is doing is they're trying to install sanitation facilities in slum communities around Nairobi. And these are communities that are not served by sanitation systems whatsoever. What Sanergy does is they have a kind of second company called Fresh Life, which is a franchise toilet model. So these are toilets that are pay-per-use toilets. Here's another example of a couple of them in a market. People come, they pay per use. The person who owns this toilet then pays Sanergy to service the toilet. If you look inside, these are what we call urine separating toilets, because when we separate fecal matter and urine, it's much easier to treat both waste streams downstream. They're also waterless, because if you're not diluting human waste, it's much easier to do something with it than if you dilute it and then try to recover nutrients again. So in these toilets, you have a urine funnel up front. There's a hole in the back for fecal matter. If you open it up, there's a jug here, that's the urine, and then feces is collected in the rear. And then every single day, this amazing team of people goes out to every single toilet and collects these buckets and replaces them with fresh ones. And it's a really complex community, and so we use a combination of like hand trucks and then to bigger trucks and then bigger trucks to then eventually get it to our processing facility. And then at the processing facility, there's a number of products that are being made from this human waste, and the main one is compost. Right? There's a lot of organic matter. So if you think about composting food, a lot of organic matter in food, we're breaking it down, we're doing something similar with fecal matter. And these are compost piles that have been here for probably 6 months to a year. And if you go and you check out these compost piles, they smell like compost, like fresh soil. They're no longer shit. They're no longer fecal matter. Yeah. And they're really excellent products. And what we did is we made sure, we monitored them to make sure that they are healthy for plants, but we also looked for pathogen concentrations and tried to optimize how we're composting to make sure. So I don't know if anyone ever's ever composted anything. A healthy compost pile generates a lot of heat, and heat kills microorganisms. And so you can kill off the organisms you're concerned about within this process. We then bagged this product and sold it under the name Evergrow as an organic fertilizer. And we told farmers where it's coming from. We did. And our marketing team went out, did farm trials, and it was incredibly popular. And so every single bag of this that is made is sold and is desired. Because in Kenya, the soils are also totally degraded. There's not enough organic matter, and the microbial community in the soils has really been decimated. And so putting compost in the soil has helped farmers actually rejuvenate their yields. It's been pretty exciting. Okay, so that is just a really tiny snapshot of the work that we do as environmental engineers. I would say we have another professor, Dr. Appel, who's an environmental engineer, and she works more on industrial contaminants and Superfund sites and sort of remediation of Superfund sites. That's another area of expertise we have in our department, but there's a ton of different things that can be done within the field. Before we leave, we've recently, as a field of environmental engineers, tried to come up with priorities for this century. As modern day environmental engineers, what are the biggest challenges that we need to tackle globally? And these are the ones that we've come up with. One is to sustainably supply food, water, and energy. And there's this thing that we're calling the food, water, energy nexus, because you need a lot of water for growing food. There's a lot of energy in supplying water, in getting food to people, there's energy, etc. So how can we best manage this nexus of these three things? We want to definitely work on climate change. So, environmental engineers work on climate change mitigation and adaptation. And there's a lot of changes that are going to happen globally that impact air, water, food, etc. So this is something that we're acutely aware of and working on. We would love to be able to design a future without pollution and waste. We want to create efficient, healthy, and resilient cities. And we want to work on these systems approaches to highlight the links between the environment, human well-being, and prosperity, and promote decision-making. So this is the big policy aspect that we're concerned about. So what I want to offer to all of you, so I hope that some of you are interested in civil engineering as a field. We're all available to you if you have questions, if you want to know more about the department. But whether you decide to be a civil engineer or not, we offer a minor in environmental engineering. That is 5 classes, totally doable. They're really interesting. 2 of them are open electives that kind of span the range of things that I talked about. And a lot of the classes that you'll take, even in other engineering majors, can serve as prereqs for our minor. So chemical engineers, we have had a lot of chemical engineers that are interested. SUE majors, absolutely. Just make sure you have the prereqs, and I'm happy to talk to you about it. Mechanical engineers, definitely, and I haven't really seen computer scientists or electrical engineers in the minor yet, but I'd love to have you. I have lots of questions that you can help with. So that being said, if you are interested,
Good afternoon, everyone. So my name is Joseph Chow. I'm assistant professor in the Department of Civil and Urban Engineering as well. I'm also the Deputy Director for C2 Smart University Transportation Center based here at NYU. And I'm also the faculty advisor for the transportation minor that you guys can choose to take even if you're not in civil engineering. So I'm going to talk to you a little bit about my area of interest, which is transportation, particularly transportation systems. So transportation is pretty, itself is a pretty broad field that covers, you can do pavement design, you can look at air transportation, you can look at bridge construction and so forth. My interest area is dealing more with design of combination of infrastructures within a city in the network context, how they interact with each other. Looking at the design and operation of traffic and transit. So how do you manage and operate these types of systems? And looking at the consequences on interactions with humans, right, in societies. Looking at the policy analysis. Questions like
whether congestion pricing, charging people a charge to get into Manhattan, which is something that they're considering right now, would that be viable, or how do you design a policy like that to be most effective? Or looking at charging taxis, or looking at different policies that could impact people of different populations. All right, so and a large part of that also relates to technology as well. Right? So we're looking at different types of emerging technologies, looking at self-driving cars and how they can be used as personalized transit services, or looking at the way that we can develop platforms to provide services for people to share resources like shared bikes or shared vehicles and so forth. Why does our work matter? It is a major issue in terms of accidents from transportation is a leading cause of death. And the fact is that as economies grow, we drive more, we also travel more. So there's this correlation where we end up having more mobility at the expense of all these other externalities like safety, accidents, as well as environmental impacts. Right, so our role here is to try to mitigate a lot of that, and the question of how to do that really requires us to look at different societies in a different way. Right, so this is also just kind of illustrating some of the broad impacts of transportation. On this picture here, you can see some of like the emerging technologies that is not just looking at vehicles and the road. We're looking at let's say integrated fare management. We're looking at smart parking, real-time traffic management, a lot of different interconnected technologies that's evolving now because of Internet of Things is an area that we're looking at. Right? And so typically we our field is based in civil engineering, but we often get a lot of students that work in electrical or computer engineering, computer science, that are also very interested in finding applications of their work that can really benefit society, right? For looking for social good applications. So transportation is definitely an area that we try to show that this can be done. Right? This is an image of New York City in Manhattan during the period of Hurricane Sandy, where we can see that when you're keeping track of data, looking at like taxi movements, you can actually see and monitor how the traffic patterns are changing significantly during that period. So we develop a lot of these kind of analytics to try to analyze and understand the way that our societies can cope with extreme events, right, like these kind of disasters, and how we can better help the society to be more resilient against them. We also look at looking at these issues of social equity, for example, the fact that when you take taxpayers' dollars and try to invest that into transportation systems, the benefits are not distributed equally across the population. And so we try to find ways to make that more equitable for different groups of the population. My lab itself, we do a lot of different aspects of transportation systems. So we do a lot of simulation work because these transportation systems tend to be very complex. They're very large scale. And so it's not trivial to try to just come up with solutions and come up with designs. We need to evaluate these designs using these kind of simulations, often at citywide level. So we have our in-house citywide multi-agent simulation that we developed for New York City that we can use to evaluate new transit lines, congestion pricing, other types of policies. And this simulation is evolving. We're adding new pieces to it and trying to make it a really useful tool for policymakers to apply to answer questions. We also develop a lot of algorithms on our own to optimize and operate these types of mobility services. Right? So this is just illustrating some of our work in looking at rebalancing car share vehicle fleets. This is a project where we collaborated with BMW Reach now, where they shared some of the data with us when they were still operating here in Brooklyn, so that we can consider the scenario of operating the fleet with electric vehicles. Right, because we want to provide more sustainable electrification kind of solutions. This is illustrating some of the work that we've been doing, looking at taxi behavior and trying to understand how these kind of mobility services can provide better, more efficient solutions for travelers. This is just illustrating some of the kinds of complex scenarios that we can look at, and oftentimes these scenarios relate to urban planning as well as economics, right? So questions like whether or not companies, mobility companies can work together with public agencies to provide better solutions for society. Oftentimes, those goals, the goals of the private companies and the public agencies will conflict, right? Because the private companies want to maximize profit. That's in the nature. But if they're developing solutions and their business model is to try to provide services and goods for society, then public agencies have a role to play to try to facilitate these companies to work together. Right, so we're seeing a lot of these kind of questions being raised now by New York City agencies and trying to better work together with these companies. So my presentation, I don't go too in depth with like showing different types of work that we're doing. I wanted to show a little bit more about some of the courses that I offer, some details about the minor, and then I'm going to illustrate some of the students that I've been working with and kind of paths that they've been taking, so you can relate a little bit more to it. Right, so these are some of the courses that I teach here at NYU. I joined in 2015. I was teaching at Toronto before that, and although I did grow up here in New York City. So some of the courses here at the undergraduate level include traffic engineering and transportation systems analytics. The transportation systems analytics course I'm teaching this semester, it's typically offered to third and fourth year students, but it looks at policy analysis, transit operations, and systems engineering. At the graduate level, I teach courses in urban transport and logistics systems. So this is really digging into the modeling and optimization algorithms to operate these types of spatial and mobility types of services. So we look at more of these kind of like industrial engineering or operations research methods, like network flows, network flow optimization, facility location, vehicle routing, and dynamic pricing problems. I also teach a course on public transit, how to operate and plan public transit services, ranging from fixed route services that you're probably very familiar with, but also to more personalized dynamic micro-transit services that we're seeing more and more today because of mobile technologies. And I teach a third graduate course, so I don't teach them all at the same time. Right? So like these two grad courses, I alternate them every year. The travel behavior informatics course, I teach that as a way to use data to infer behavioral patterns from travelers so that you can design systems better to accommodate them. So we mentioned that there is a transportation minor. This might be a little bit hard to read, but it's a 5-course minor. 2 are core required courses, one of which is a choice that you can take between transportation engineering, which we offer every year, or intro to transportation systems. That's offered less. And then at the end of your 5 course, you're taking civil engineering design, capstone design course in your senior year. So in between that, you can choose different electives to take. So it's very versatile. These are some suggested courses, but as a faculty advisor, if you have questions about these or if you have other courses that you think you might like to take as electives, we can talk about it and I can try to accommodate those various backgrounds that you have. But you can see there's a range of courses from even within civil, but there's often a lot of courses from like SUE or looking at technology and a society or electrical and computer engineering that would be applicable to this as well. On the website for the transportation minor, we list out some scenarios for students that if you're not really sure about what kind of courses you want to take. So this is one roadmap for a CUE student that might be interested in traffic. So you can see some courses that are listed there as suggestion. This is a roadmap of CUE students interested in public transit. This is for a non-CUE student that's interested in transportation policy analysis. And this is one for a non-CUE student that's interested in emerging mobility technologies, and they want to look at maybe some more like using like data sciences and data analytics to apply that to providing better mobility services for people. Right, so this is gives an overall picture of the minor, and hopefully if you guys have questions about it, you can come to me later about it. My lab also does a lot of research. We have grants from National Science Foundation as well as the C2 Smart Center that I mentioned. I often work with a lot of undergrads on these research projects. Right now there's a summer undergraduate research program. Are you guys aware of this program as first year students? So there's a program for that undergrad students are eligible to apply towards, where you get paid to work full time during the summer with research labs. Right? It's called Summer Undergraduate Research Program. And so this is various cohorts that I've worked with each year. The students, each summer, they work 35 hours a week for 10 weeks. And sometimes they'll end up with publications. And some of them have moved on to work with us in graduate school. These are some of our graduate students and the topics that they've worked with and where they've ended up afterwards. So you can see kind of like the range of opportunities that these students have had working in these various topics. We also have a pretty active society, student society. It's called the ITE-ITS Student Chapter. It's both because there's actually two sub-organizations there. And actually Professor Jack Ringardner is the advisor for the ITE Student Chapter. So you can definitely ask him some questions about that later on if you're interested in participating in this. We do maintain a Facebook group where we provide updates on and announcements on events and various job opportunities, internship opportunities, scholarships, and so forth related to those kind of topics. And you can see how this is a little bit old, this from the previous year, but it just kind of I'm just using this to show as an example the kind of activities that throughout the year the organization gets involved in. So you can see that it's quite busy. As far as showing some of the students, I think from your perspective, you want to see like what kind of pathways you can take if you were interested in taking transportation as a minor, or even just looking at doing a research project with my lab, right? So this is more of like a slideshow of some of the students that I've been working with the last 3 years, from either undergraduate or from masters. I left out PhD students from here. So one student is Ziyi Ma. He did his undergraduate here, and currently he's staying on as a master's student. He's finishing up. He worked with me in his summer undergraduate program and published a paper out of this as the first author. And he's been pretty integral in helping our team develop the citywide simulation, a tool that we're using to evaluate these policies for policymakers in New York City right now. And he's been involved very actively in the civil engineering department in various competitions like Steel Bridge or Traffic Bowl. He's interned at a couple of different companies, and he's taken 2 different courses with me as an undergrad, and he's taking more with me as a master's student now. Elsa Kang, she was a civil engineering undergrad, not in transportation, but she took a summer undergraduate research with me, worked in my lab, and developed a tool to convert this data from bus arrivals that you can get real time, right? But she used that to develop a tool to monitor arrivals of buses at bus stops. She's been pretty active with the ITE student chapter as well, where they've gone out to host events like a transportation camp. She was the event coordinator for the chapter, and she's currently working at an engineering consulting company. Isaiah Mwamba, he was an undergraduate from NYU Abu Dhabi. He was taking one of my courses, and then he spent the summer interning with me in my lab. I got him involved working on public transit operations planning, so meeting with like New York City Department of Transportation to look at these select bus services and the design of these queue jumping lanes. So to evaluate how much investing in those lanes can improve the reliability of the bus service. He's also participated in the ITE Traffic Bowl, which is an annual competition that the ITE student chapter gets involved in. So like they compete regionally, and then if they win, it's a Jeopardy style game, right? So if they win, they go into national level. I don't know, do you know where the national location is this year? Okay. So now the team is prepping for the next competition. And then for his research, he joined me in working on that project. After that summer, he returned back to Abu Dhabi, and he finished, and currently he's a graduate student at Purdue. Another student of mine, he's a graduate student. So Nick Carrolls, he did his master's with me in my lab, and his research topic was on modular autonomous vehicles. So he was working with this company, Next Future Transportation, to develop algorithms to simulate the performance of these services so that he wanted to evaluate what's the potential societal benefit of using these self-driving cars that can join, couple and decouple on the move. One of the advantages of this type of system is that when a passenger gets onto one of these vehicles, they can transfer to another vehicle while it's on the move. So it eliminates station platform level transfers. So there's a high potential value to these kind of services. So he was looking at this and analyzing the potential of this type of fleet in Dubai to Sharjah as a commuter link. He did his bachelor's from UBC, and he was interning at Stantec at the same time while he was working in my lab. He was actually the founding president of the NYU ITS chapter before joining up with ITE. His thesis work was featured at TEDx talk in Germany, and currently he's doing his PhD at MIT. Manel is another master's student in the transportation management program at NYU, and he was looking at this project with the Brooklyn-Queens connector. How many of you guys are familiar with BQX? Are you aware of that? No, nobody's aware of that. So this is a planned route that the city, New York City, is trying to endorse. Right? Basically, they're trying to build a streetcar route along the waterfront from Brooklyn to Queens. This is a conceptual image of, this is J Street, right in front of us, right? This is where they're planning to run a streetcar to provide better connection from Brooklyn to Queens. So he did a research study while he was doing his master's here as a Fulbright scholar. And that work has been published. He's also been participating, he was participating in hackathons, like a Staten Island bus hackathon hosted by NYU Wooden Center. And after he graduated, he was chief operating officer for Transbus Balear, which is in Spain. Another one of our students, she did her master's with me, Srushti Rath. And she was a master's student who joined, actually that's a little bit old, so she was the previous year, and her thesis topic was looking at air taxis. With all these development of UAVs and drones, there's been a lot of investment and interest in creating these drones at a scale that can use as a taxi service, right, to transport people from place to place. Uber, for example, they developed a subsidiary called Uber Elevate to provide these kind of services. And they were planning to invest in that in LA. And they were looking into that in New York City at a very preliminary level, but they were at least setting up, there's an Uber copter here now, I guess, in New York City. So she was looking at this and developing optimization algorithms to locate hubs for the skyports for these air taxis so that they can be used to transport people more efficiently, right, determining where to place them. So after this project, I hired her as a research assistant to work on a study with the Federal Transit Administration. Uber also hired her as a summer intern in San Francisco, so she spent her summer working there. She's currently a PhD student with me. She just started in the spring. Last one. Okay, so Mandy Lee. She's currently an MS student at NYU studying transportation. Her thesis topic was on school bus routing, which you would think that school buses are pretty easy to operate, but it's actually quite challenging because you have to design these routes to accommodate student schedules. They're pretty large scale, and if you mix in special ed needs from students, it can be more complicated to try to design routes to accommodate that. And so she's been looking at using various tools like Google OR tools to solve these kind of routing problems. She was interning at the New York City Department of Education, and she's starting at an engineering consulting company after the spring. So that gives you a kind of like a snapshot of some of the students that are the pathways that they've taken when they're interested in transportation, at least at the undergrad and master's level. There's a lot of opportunities in transportation given this mix of technology, societal need, and the combination of the goals for sustainability and livability, and the challenge of overpopulation and urbanization. So transportation is kind of right in the mix of all of that, and it's very interdisciplinary. So when I was an undergraduate student, I also wasn't very sure about what topic to focus on. I was just a general civil engineering student. But then after I finished my undergrad, I decided I wanted to do more transportation problem because of that kind of interdisciplinary problem-solving aspect. But definitely, we encourage more students to be involved. And if you're interested, transportation minor might be a very good option to consider. Or at the very least, if you would like to just talk about it, you are welcome to reach out to me. So this is my contact information. My email, you can find me at 15 Metrotech, 6th floor. There's a computer lab there called CG Smart Lab. My office is right outside of it.
Hello everyone, I'm Semiha Ergan. I'm a faculty in Civil and Urban Engineering. I joined NYU 5 years ago. I was a PhD student at Carnegie Mellon University, and I was a research faculty for a couple of years there, and I'm returned to here. So what I want to do is I want to give you an overview of what types of research areas we focus on as a civil engineer. And you're going to hear from many of us today in terms of once you have a degree in civil engineering, in what areas and what connected areas you can continue working on and keep learning. So I'm not sure what this can be done is, but in general, when we, in my research group, we're looking into several things. First one is looking into how we can improve the design and construction processes by using different data sources and particularly IT, information technologies. And when I say information technologies, these are ranging from data models that can include a lot of semantic data, as well as technologies like laser scanners, where you can get millions of points that represent a 3D world around you, where you can get more accurate data about the construction project. So in terms of improving work processes, we're looking into, particularly from construction perspective, one of the challenges is that when you bring all the people at site to start building a particular bridge or a highway or a high-rise skyscraper, etc., one of the challenges is that you want to make sure that you build it right at the right when the thing's supposed to start, right? You want to minimize rework, you want to minimize requests for information, so you want to minimize change orders that typically happen at construction job sites. One of the ways to do is use building information models, which are 3D representations of the whole project digitally. And it's not just 3D data that you are looking into, it's a lot richer data that you are representing and exchanging When I say a lot richer data, meaning that when you look into a wall knows its properties. So if you are coming from the CS background, or if you had any programming class, you can think about this as data attached to the geometry. So if we look into the whole life cycle of a civil infrastructure systems, right? If you consider the costs that are shared by different parties throughout the life cycle of that facility or the civil infrastructure system, if you consider this $1 as the cost of waste that is generated, so around 20% of that $1 is spent during planning, design, and engineering phase. Around 25% of that $1 is spent during the construction phase. And the rest of that money is basically on the shoulders of the owner and the facility operators who needs to manage and operate that facility for the rest of its life cycle. Okay? So the important thing is that, yes, the cost of inaccurate interoperability, meaning the data that you need during the design phase or the data that you need during the construction phase, and the data that you generated during those phases that you will definitely need during the operations phase are not always properly packaged and then shipped to the owners, and they keep facing the challenge of figuring out where those valves are to shut off, where is that fire sprinkler connected to, several other building components that they need to trace to figure out maintenance issues and solve problems. So in general, we utilize building information models to provide accurate as is facility data or civil infrastructure data that are represented in building information models. From a research perspective, what we do is we use these data sets plus the sensing data coming from these facilities, like if you're looking into a bridge can have various sensors associated with it that gives the performance of it over time. Or if you're looking into a particular building, you're looking into building automation systems that gives us a lot of sensor data in terms of how this particular system, like the heating and ventilating system, is performing. We have smart meters nowadays in our buildings that gives us what's the energy performance of that building too, right? So what we do is we integrate these building information models with those sensor data and look into how we can improve the performance of buildings from an energy perspective. So we also do this prediction of energy use over time, providing that information to the facility operators or the occupants so that they know how much they are consuming in terms of energy and how they can benchmark their use with respect to the other tenants, etc. Again, from using building information models, we are looking into how we can improve the system's performance. Particularly, we are aiming at heating, ventilating, and air conditioning systems. And we are looking into how we can do fault detection and diagnosis using the data represented in models plus the building automation system data. Also, how do you compare the performance of a building with respect to its current state and how it was supposed to behave? So the design tells you the characteristics of how it should be operated versus the sensor data tells how it is actually operated. Can you compare those and figure out what are the violations in terms of controls, and you basically look into comparing design intent with respect to the actual building controls. With using, again, building information models, the other aspect is you can visualize the data. And nowadays, visualization is an important thing to look into the facility data. So one of the ways that we visualize and provide support to facility operators is using laser scanners, which provide that massive 3D points. When they come together, it looks like this. What you see in this video is the 3D world. Actually, what you're seeing is not a real space. It's a bunch of points coming together that looks like the 3D world. What we do is, once you capture a point cloud data, you can compare it with an existing model that was generated maybe 10 years ago when the construction was over, and you can overlay these to figure out deviations over time that happened with a lot of renovations, right? And provide what are the things that facility operators should be aware in terms of changes that happen over time. So that's an active research area that we are focusing on. In terms of accessing to, again, facility information and improving the situation awareness of these facility operators, we do provide, look into different ways of what's an effective way to provide the same information to the facility operators. So we're looking at all the way from representing the same sensing data with the spatial orientation on the 2D, 3D, taking it to virtual space, or taking them all the way to the immersive virtual setups where they feel immersed and then they can do virtual planning or maintenance even in the virtual space. I will skip those because these are some research challenges. So here is one of the examples that we use to bring the sensors back to the spatial context where they are generated. And this is the Phipps Botanical Garden in Pittsburgh. And we use this as a test bed to figure out if we can improve the situation awareness of the facility operators in terms of what the sensing data is coming. So that's what they typically see when they look at the screen versus we embedded those data, streaming data to the 3D representation to see if there is any value of showing them the data in the 3D space in terms of ignoring some of the alarms versus accepting those alarms and acting on those. Other ways to look into the visualization aspect and improving the decision processes. This one is particularly was looking into how we can use immersive visualization to improve the design process. When you look into a design of a civil infrastructure system, there are various parties involved, particularly for buildings. You will see that architects are on board, civil engineers are on board, the mechanical engineers, electrical engineers, plumbers, etc. All of them are on board. And how do you make sure that you can bring all the design data together and then make sure that their assumptions when they were creating those models are clearly conveyed to them, and then link all of these back to the overall life cycle performance of that facility. So it basically is a way to improve their design decisions. From, again, the perspective of using building information models, we look into how we can do model-based troubleshooting whenever there are work orders. So if you feel too hot or too cold in a room, typically you will call the facilities office and say, create a complaint. These complaints are called as work orders. So you will receive that work order, and then as a facility manager, you need to know where the problem source is. So by integrating the historical work order data sets with the model information, you can basically start reducing your search space in terms of what could be the possible causes of a problem when you receive it. So that's an active area of research that we're dealing with as well. Again, in terms of visualizing, we use virtual reality, which basically you convert a given model into, say, bringing it into a Unity 3D environment to create a virtual space. We use them to obtain the requirements of facility operators when the project ends. So whenever a construction project ends, the general contractor who builds the facility submits the drawings to the owner, but nowadays part of the contract requirement is to submit a building information model. And the owners suffer in terms of what they should be asking in a building information model as a submitter. So we use virtual reality in this case to reach out to around 40 facility operators to figure out what those information requirements that they would have from an asset management perspective, space management perspective, or maintenance. And we use virtual space to embed them into and then figure out what are those information items that they would need in a realistic setting. Beyond these, what you can do, it's like a big playground. Once you have that building information model as a semantically rich data representation, you can keep adding on it to help other decision support processes. For example, one of the current projects that we are doing in the lab is, can we improve the design by looking into and measuring how people feel in a particular space? For example, when you are sitting in this auditorium, you might be sad, you might feel bored, you might be anxious, right? There are sensors that nowadays, non-invasive, that you can basically wear on your body, and it keeps tracking the data about your physiological states, like whether you're sweating, whether your muscles are, you're frowning or smiling, your heartbeat, your brain signals. So in this particular project, we brought all these sensors together and then defined it as a body area sensor, like eye tracking, EEG looking into brain signals, GSR looking into skin conductance, whether a person sweats or not, and then prepared these virtual reality setups where they were immersed in different versions of the same design, and then we were looking into which one of these design options people feel better. And when I say feel better, this is in terms of whether we're measuring stress and anxiety, motivation to work, or restorativeness. So we looked into several different things. And the overall idea is, can we figure out those design features, like the number of windows in a space, luminance level, right, artificial lighting versus natural lighting, and which one of those are more impactful when we're looking at designing spaces. And if there's a feedback loop back to the designers and architects in terms of, hey, you can focus on these features more because they are tied to better human experience in spaces. So, in a nutshell, that's what we do, but even if, one thing that I want to say to all of you is that if you are in an engineering field, eventually you will figure out that there is much more that you can add on to your basic bachelor's degree and then move on to other fields and collaborate with other people that you never thought of you could be able to collaborate. So the opportunity is out there. Just keep doing what you're doing and study.